Hello, everybody. Thank you for attending one more telecom seminar, which is hosted by the Technology Innovation Institute in Abu Dhabi. This kind of activity has been organized on a bi-weekly basis. And for today, we are pleased to welcome Professor Mohamed-Slim Alouini from KAUST in Saudi Arabia as the speaker of this telecom seminar. And his today's talk will focus on the digital divide that exists in the world. And he will discuss on how our free space optics in conjunction to satellites and high altitude platforms can help on this. Actually, I think it's very difficult to believe that nowadays with 5G being implemented worldwide, there are many people, almost 4 billion people on the globe who are still unconnected or underconnected. And maybe this is because the previous generations has primarily dedicated to satisfying the application scenarios in urban areas where with a dense deployment of telecommunication infrastructure. And for the next generation, I think we hope that 6G can give more attention to these low-income regions with much less population, physical infrastructure, and limited financial resource. So this is a very important research topic. I'm connecting the unconnected. Professor Alouini has made hard efforts in this topic, has published many seminal works, has also organized some events on this theme. For example, I attended the last 6G Summit organized by KAUST, connecting the unconnected. And okay, but before moving to the talk, let me say some few words of Professor Alouini. Actually, he needs no introduction. I'm confident most of you know him very well. He's a very famous professor of our scientific community. And personally, I have him as a model to be followed in my career. So actually, he published many papers. For me, it's very important that he has a very famous book called Digital Communication over Fading Channels. And this book inspired me a lot during my graduation studies almost 20 years ago. But let me say some further words by reading his biography. So Professor Alouini, Mohamed-Slim Alouini, was born in Tunis, in Tunisia. He received the Ph.D. degree in electrical engineering from the California Institute of Technology, Caltech, in 1998. He served as a faculty member at the University of Minnesota, then in Texas, University of Qatar, before joining in 2009 the King Abdullah University of Science and Technology, KAUST, where he is now a distinguished professor of electrical and computer engineering. Professor Alouini is a fellow of IEEE and OPTICA, formerly the Optical Society of America, and he is currently particularly interested in addressing the technical challenges associated with this uneven distribution, access to and usage of information communication technologies in rural, low-income, disaster, and hard-to-reach areas. So, Professor Alouini, thank you very much once again for accepting the invitation. It's a great pleasure for us to have you here. And now the floor is yours.
Thank you very much, Daniel, for this invitation. Thank you, TTI, for giving me and my group the opportunity to present some of our recent work in this area. I will stop the video because it seems that we don't have a very stable connection, and I'm trying to make sure that we keep the connection on, so I'll try to minimize the bandwidth. So I'm sharing my screen. I hope that you all see my screen. So as Daniel mentioned, this topic is about connecting the unconnected and essentially how free space optics can help in this context. You know, as you know, we are all now working on beyond 5G and 6G. This is normal. as 5G is being aggressively deployed worldwide. We have this decade to develop beyond 5G and 6G, with the hope that by 2030 or by early 2030, we start seeing some of the early version of 6G being deployed. Of course, many researchers are focusing on the kind of a pushing envelope type of objective of beyond 5G, which is getting internet faster, getting internet, let's say, reach some area with the lower latencies for ultra reliable, ultra low latency type of application, having more density of connected device per coverage area is another objective that people are pursuing. But there is another interesting aspect that sometimes is neglected, which is basically that we need to make sure that internet reach more places worldwide. Since we still have a situation where about it's a number that is around 3 billion people, sometimes even a little bit more, depending on how you count them, that essentially are either completely not connected, so they don't have any internet connectivity, or underconnected, which means that they have, let's say, a 2G type of connection, which is not good enough to take a full benefit of internet. So obviously, this is an important challenge that, as I mentioned, was not very well addressed by previous generation of wireless communication systems. And there is now this objective to try actually to hopefully address this big problem, especially that we have seen the importance of internet during the COVID pandemic time and the lockdown type of situations. So we want to break this vicious cycle of connectivity or digital divide, where you have areas, typically rural areas, typically areas that are remote or hard to reach, that are suffering from weak development and growth, and that are basically unconnected or underconnected because of this kind of weak development, and that kind of lead to this vicious cycle. So if we are able to invest in these areas, connect them, create highway of information, we can improve their prosperity by giving the population residing there better access to health services, education services, financial services, like many in this area argue that connected and unconnected can help also bank the unbanked. So there is a full cycle of opportunities that can open if we're able to connect these unconnected. But beyond that, I mean, beyond just connecting the unconnected, if you are creating this nicely connected environment that are not necessarily this urban environment, then actually we can incentivize people who are currently living in congested, let's say crowded urban environment to migrate back to rural environment and keep doing their job remotely because they are well connected, which means this can trigger a counter urbanization process, which is much needed in view of the projection of these many more mega cities that the world is going to kind of see if things continue the way they are evolving these days. So this can help make the world a better place by evenly distribute population in area, and rather than basically making infrastructure that kind of make them all trying to live in congested downtown or urban environments. In other words, we want to move from the narrow concept of, let's say, a smart city to something broader that we can call smart villages, smart hamlet, smart rural areas, in general, smart living, where basically everywhere or many environments are connected and people can live seamlessly in all of these environments and have pretty much the same type of benefits. So what are the issues? I mean, why are we having these problems? One of the main issue is a backhaul problem. So this is summarized in this kind of view graph. So here we are illustrating the quality of experience. It can be measured, for example, in the data rate and low latency. These are kind of measure of quality of experience that someone can observe as far as the cost per user in remote low population density area. So obviously, if you go for optical fiber cables or even point-to-point microwave wireless link, you may have a good quality of service, there's data rate, but this is quite expensive. As you know, it's very well known that it does not make much business sense for a mobile network operator to, let's say, dig and kind of lay 100, if not thousands of kilometers of optical fibers to reach very remote kind of rural areas. This doesn't work from a cost perspective. If you go to this particular corner, you see that satellites are affordable, but have been used essentially because of the broadcast nature of the early generation of satellite communication for one-way broadcast type of situations, which is like for TV broadcasting. But as soon as you start talking about internet browsing, the two ways, uplink, downlink, then it's not cost effective anymore. So the problem we're trying to solve is to place ourselves in this upper basically left corner, where you would like to have very good quality of experience, but we would like this connectivity to be very low cost. Okay, so that's the holy grail of global connectivity that we are trying to achieve in order to, let's say, fulfill this prophetic vision that Nikola Tesla had 100 years ago. And if you read that statement carefully, you would see that Nikola Tesla was thinking already in a 5G or 6G terms 100 years ago. So that's our objective. And to reach that objective, we need to design a system in a completely different way than the way we design them in congested downtown areas. So in congested downtown areas, we all learn that we need to reuse aggressively the spectrum. We need to go for small cells. We need to basically capitalize on this kind of strong reuse of the spectrum to deploy many small base stations throughout our urban deployment. Now, when you go to these rural areas where you have a very light density populations, you need to go the other way around, and you want to have basically super macro base stations. So one way to do that is to reuse the TV tower, let's say, because typically they are placed on the top of hills or mountains. You can even use the spectrum that has been given for TV towers, prime spectrum, VHF, UHF band, in order to create these macro cells and capture as many users as possible within this 30-40 kilometer range of people living in this area, because typically it's a low density area. So recently, Dr. Ammar Al-Falou, one of my group members, wrote an interesting magazine paper that is still going through process and it's available on archive, that basically illustrate this concept, which anyway is not the first time this is being proposed, but it's kind of give the philosophy of going against the design in urban area with small cell towards like big macro cells. So that's one option. Now, if you want to gain in altitude and similarly gain in coverage, you can go a little bit even higher and go towards this kind of tower in the sky, if you will. This can be achieved through tether balloons or tether aerostat. These are blimps, if you will, that are filled with helium or any kind of other kind of gas that is lighter than air, so they can stay aloft. They are typically connected with a tether to the ground. The tether is there to provide a backhaul, through a fiber optic insert within this cable or tether, and it can also provide the power. And again, you can attach an access point or a base station to this tether balloon, and you can get tens of kilometers of coverage thanks to that. So that's another way to achieve bigger coverage or create macro cells in rural environments. You want to go even further, you can go higher. And then we start talking about HAPS. So probably heard about this term now. HAPS stand for high altitude platform stations or high altitude pseudo satellites. We had few paper on that. I'm citing one of the paper from our group members here that talks about HAPS. So HAPS basically are a platform that are flying at the stratosphere at roughly 20 kilometer altitude, just for calibration point, like airplane, they typically fly at 10-kilometer altitude. So when you are at this kind of twice the height of airplanes, you can have even a higher coverage area. People talk about roughly 200-kilometer radius coverage area that can be achieved with HAPS. And you can attach again to these HAPS a base station or an access point. And some experiments have been done where basically 4G and even 5G type of connection were being established with direct connection to HAPS. So that's the beauty of HAPS. You don't need special infrastructure. You can still associate to them a regular base station, and the user on the ground, he or she doesn't know that he's connected or she's connected to a HAPS. It's using the standard phone to make a phone call or like internet connection, but it happens that the base station to whom he or she is connected is attached to a HAPS. So it's an interesting topic. HAPS can come in different colors and form. They can come in the form of balloons or drones, like the Zephyr or Aquila project of Facebook, as illustrated in the picture here. But this is beyond the scope of this presentation. The idea here is that that's another solution that can help us basically connect from the sky. Now, the ultimate solution obviously is to go even higher, and here we start talking about the space type of solution, and satellite of course give a much bigger coverage than any other solution provided earlier, but then they are not typically access solution. They are backhaul solution because it becomes hard from a budgeting perspective to connect direct to a satellite. So a satellite is there to connect in an integrated ground airspace fashion, user on the ground through maybe a relay that can be a HAPS, for instance, to the rest of the network, to basically the connection to the rest of the network can happen through gateways. So you have a feeder, what we call the feeder link. The feeder link is a connection between satellite to the internet backbone, and the user link can be just a collection of multi-beams. And here you can start using the concept that we have been using in urban congested area where the spectrum is being reused. But on the ground, typically you don't have user using their standard cell phone. Rather, we have a very small aperture terminal that can act as relay, that can create Wi-Fi hotspots or 4G, 5G connection, and the ground user can connect to that kind of a VSAT, and via that VSAT antenna can connect to the satellite and eventually to the internet. So these are the different layers, and what make things quite interesting these days is that these layers are supposed to work in harmony, or in other words, what people are kind of advocating for is kind of integrated ground. And here we talk about, the standard user connect to the ground, the base station, the access point on the ground, air. And here we talk about UAVs, drones, all the way to, balloons, tether blimps, tether aerostat, and eventually basically HAPS. So we are still in the air type of layer, type of connections, and then eventually space or satellite. And when we talk about satellite, we have the different family of satellite networks, and by that I mean LEO satellite, MEO satellite, and GEO satellite. So all of these layers, we don't have to use all of them for all application, but you may use few of them or different layers in an integrated fashion to create your full network that is going to help service and make access available to user on the ground. So this is kind of summarized. This is what I'm talking about is summarized in this kind of view graphs, where you see the different solution I have been talking about in an integrated fashion. So you have the HAPS, you have the blimps, and so on. And my talk is going to kind of zoom on some of the interesting research topics that we have been pursuing over the last couple of years on these topics. Now, before getting into the technical part of the talk, I would like to highlight that obviously we always have also to remember that we do have a spectrum scarcity problem. Spectrum is a finite resource. It's typically optimized by the government in view of the many applications that are out there. And as we use more and more spectrum for a variety of applications, there is also this kind of competition for using the spectrum for aerial, space, and ground type of applications. So typically these applications have different part of the spectrum, and because of the fact that every one of these applications is growing, there is less and less spectrum to distribute. And therefore, here we are advocating to move to the optical band because there is plenty of spectrum available there. When we talk about optical band, there is the infrared, the visible, the ultraviolet. We're not going to talk about UV or visible here. Let's focus on the infrared or free space optics. I'll be a little bit fast here. I would like to focus on the free space optics type of connection in the context of satellite and aerial type of connection. So it's point-to-point for backhaul type of applications, where basically FSO can be a great help to kind of relieve the spectrum congestion that we are having, and we expect to have more as we move forward. So here is how free space optics works. Those of you who are familiar with it, and maybe some of you have attended a presentation done a few weeks ago by Professor Robert Schober. He talked quite a bit about FSO in the context of also FSO with the help of IRS. But typically FSO is there for point-to-point, high-speed communication. It can give you super high speed. It can be implemented for ground type of application, but also for ground to air or ground to space applications. But it does suffer from two key kind of issue: atmospheric turbulence, that we'll talk more about as we move forward, and alignment and tracking. You want to make sure that the laser is pointing perfectly toward the photodetector receiver, and if that doesn't happen, then you lose the link, and with that you lose the SNR drops drastically, and you lose the whole connection. So these are the two issues we'll be talking about in this talk in the context of ground to air and ground to space communication. So it's essentially, this is not science fiction. It's being pursued by a few research groups worldwide, where FSO is being used to connect either UAVs or basically HAPS or even satellites. So here the typical application we are talking about, like let's see here we have a very high throughput satellite. It can be, let's say, even a geostationary satellites. It can have a two side, what we call a user side. These are multi-beams that can be moved around and can go where traffic is needed from a user perspective. The user can be having, let's say, a very small aperture terminal that can create a Wi-Fi access point or like a cellular type of connection in the neighborhood. And then the satellite is acting as relay. It needs this feeder link that connects to the ground and provide internet connection to all the users. So currently, most of these feeder links are being done for high throughput satellite are done in the Ka band. By the 2030s, it's expected the Ka band is going to become, let's say, saturated. Part of it can move to IMT or cellular type of users, is like in the 28 GHz, for example. And also some of it can be used to the user link, which is currently using more Ku band. So the argument here, or the plan, or the proposal is to use basically optical feeder link or free space optical links to connect the ground to satellites. Of course, you need to kind of solve many of the challenges that you'll be facing on your way. One of the challenges is, we'll talk about them later on, turbulence, alignment, but also weather conditions. So if you have a cloud on your way, this is going to block your FSO type of link. So you need to have a network of optical gateway station on the ground. We call that site diversity, so that if your signal is blocked by one of these optical gateway station, then basically it is recovered by another optical gateway station, can be even in a different country. So it should be kind of a consortium of let's say countries that can unite together to create this optical gateway station network in order to make the full network reliable. This same concept can be used for HAPS. We can call these, by analogy, very high throughput HAPS, where again you can have user link that can have different type of beams. The HAPS can have a radius of cover up to 200 kilometers, let's say. Some of these beams can be used for offloading purposes in downtown areas. Some other beams can be used to connect rural areas or villages, or even maritime type of communication with boats and yacht or IoT type of device in an underwater or in a marine environment. So basically, again, that's the user part or the user link part. You need a feeder link, and this feeder link can be done through an optical FSO feeder link, high-speed FSO feeder link, in order to save spectrum. So that's kind of the typical application we are talking about. So just to kind of open the floor, let's say for the next part of the talk, you know, an FSO type of channel is quite simple from a modeling perspective. What you have a signal, you have the optical electrical conversion coefficient, and you have this irradiance that is basically a random variable reflecting actually not only the fading as mentioned here, but also the pointing errors, the absorption that you can be subject to due to you know, maybe low visibility like haze, like cloud, like fog, etc., plus some additive noise. Now, the key point is to model this fading here, or this kind of random variable, and we'll be focusing here on the two aspects, the atmospheric turbulence first, and then the pointing tracking error problem later on. So atmospheric turbulence, you know, there is a full theory behind that, where basically when you propagate over when an optical wave propagate in turbulent environment, there are eddies of different scale that generate what we call small scale turbulence and large scale turbulence. This lead to different kind of effect. One of them is a so-called beam spreading. The other is beam kind of wandering, and the beam spreading leads to the kind of received signal or received beam becoming like blurry, if you will, and then this kind of beam wandering can lead to this beam dancing around at the receiver end, and that's in part the reason for this pointing error that you are subject to at the receiver end. So you know, this kind of again turbulence that lead to this fluctuation of the signal. At the end of the day, from a detector perspective that is at a fixed location, what we are subject to is scintillation, or basically signal kind of fluctuating over time. This is typically characterized by a famous random variable, although there are different models. You can use log normal, you can use a negative exponential, you can use the Weibull exponential model. There are a variety of, let's say, distribution have been used to model turbulence. One generic model is a gamma-gamma turbulence model. The beauty of this model is that it can cover a large range of turbulence environment from weak to strong as a multiplication of two gamma random variables. It happens that this is well known for the wireless comm theory community, that when you multiply two gamma random variable, you end up with a gamma-gamma, which is a distribution that is well known in terms of the modified Bessel function of the second kind. And it's parameterized by the two parameter alpha and beta that are function of the rate of variance. This rate of variance is for a fixed altitude and a fixed wind speed. It's function of the link distance. So the more the wave propagate, the more the rate of variance increase, and the more turbulence you are subject to. And typically, but obviously, if it is, for example, over slant path, let's say from ground to space, you need to integrate this rate of variance over the whole distance in order to get the final value of the rate of variance. Here, I'm looking at like for, let's say, a horizontal link, but for a slant path, Cn will be function of the altitude and actually the wind speed. So you need to integrate that to be able to get the rate of variance. And the result, if you end up with a rate of variance that is much smaller than 1, we talk about a weak turbulence regime. If it's roughly around 1, it's a moderate turbulence regime. If it's much bigger than 1, then it's strong turbulence regime. And if you plug these rate of say numbers into alpha and beta, which are the gamma-gamma distribution type of parameter, you end up basically, for example, for weak turbulence where the rate of variance is 0.2, you end up with a gamma-gamma with a very light tail, which means that you have a typically good performance. Then for moderate turbulence, you go to blue. You start having a kind of a higher tail near 0. And then if you have strong turbulence, let's say sigma r of the order of square of the order of 3.5, then obviously you have a much higher tail near 0, which means you have very bad arch probability or meteor rate performance, because a lot of the fading is around 0. So we'll be using gamma gamma in what I will be illustrating today, but again, there are many other models that have been used. Now, one way to mitigate the effect of turbulence is to use so-called adaptive optics. So adaptive optics is techniques used to, let's say, correct the waveform, because what turbulence does, it kind of, introduce distortion in the wavefront. Is kind of like a transfer function, and the adaptive optics will give you the inverse transfer function end to end after this correction. This correction can be done through, let's say, an array of deformable mirrors or a liquid crystal display. It can be done either at the end of the link in a post-compensation fashion. When you have learned what the distortion is, you can try to compensate or distortion or to get a corrected beam, or you can do it in a pre-compensation fashion. If you have a beacon Gaussian beam from the receiver with the feedback, you can pre-distort the beam so that once it goes through a turbulent environment, you end up getting a nearly pure beam. So why I'm showing that? Because we're able to model that, and this is based on the kind of very famous book of on FSO that basically explain how adaptive optics can be modeled in the Kolmogorov spectrum. So basically, once you have a Kolmogorov spectrum that is being, let's say, or a link that is being corrected by adaptive optics, you have a different expression for the spectrum, for the Kolmogorov turbulence spectrum, and this has been included in our calculations, and you can see that we get some gains thanks to adaptive optics. So for the position acquisition and tracking, the issue is a very classical issue that has been looked at for many years. So essentially, in theory, what you would like to see is that the beam footprint is in complete alignment with the detector. But in practice, what we'll see some vibration in the horizontal, some vibration in the vertical dimension, and then you have this kind of error R. So this error R, which is square root of x squared plus y squared, where x is a displacement in this direction and y is displacement of this direction. The idea is to minimize R, but you will always end up with some residual R, whatever you do, because you will always have some errors. So some of the work we have done is trying to minimize this R, and you can minimize at different stages. So it is pointing, acquisition, tracking. So here, for example, in this paper we wrote a few years ago with Dr. Salman Bashir from my group, we looked at how we can minimize acquisition time. And one way that is well known in the community, because you can use shotgun approach, you can use zigzag type of approach, and people experimentally have been using the so-called spiral approach in order to lock on the signal. So we try to model that, and we try to look at the total acquisition time using the spiral approach. So you can see the acquisition time is equal to the scan time. So the scan time is the time it takes you to scan the whole area. Typically, it's 3 times the variance of the pointing error. Times x, which is the number of time you do that. Now, it can happen that you lock on the signal, but you don't realize that, because sometimes you have a misdetection, because you may have lack of sensitivity of the detector. So you need to go through a full scan because you didn't detect that you locked on the signal. So that accounts for the first term accounts for that. Plus the second term is the kind of the scan where basically you are successful. Then basically you don't go through the full scan of the whole area, you go only a fraction of the spiral, and TD is a dwell time, which is the time it takes you to kind of shine an area and wait to see if you lock on the signal. Time W, which is a fraction of time in the last successful attempt, so it depends where you stop in the spiral. So all in all, the first random variable, as you can see, is like the number of failed attempts until success. So it's kind of a geometric random variable. And TDW, it turns out that, actually W is an exponential random variable because of the fact that we assume that essentially the vibration, the x dimension are Gaussian and the y-dimensional Gaussian. So like the error is really, and the square of that is exponential. So bottom line, V is an exponential random variable, and you end up modeling this acquisition time as a sum of a geometric discrete random variable with a continuous exponential random variable. You can do the math, and you can end up having as a convolution the distribution of the acquisition time, and then you can derive even the complementary CDF. And with that, you can see the violation time, which means when would it take you more time to lock on the signal beyond a certain deadline. Now, just to make a long story short, here we kind of try to look at this complementary CDF of the acquisition time as function of the noise power for a variety of number of receiver, because here we are using an array of receiver in order to improve our sensitivity. And obviously, the more receiver we put on our photodetector, the better is our, let's say, performance, because we lower this probability of failing to acquire within a certain deadline. But then the other interesting result is looking at the basically acquisition time as function of the beam radius. So this is something you can control. And obviously, if you make the beam radius or beam, let's say, diameter bigger, then you can scan this whole area faster, right? And that's why basically as you increase your beam, what happens is you will go quickly, you decrease your basically acquisition time. But then at some point when the beam becomes too big, then you will lose starting in sensitivity. So you'll start having a lot of misdetection. And that's why there is a nice sweet spot here for any number of detectors, M1, 4, 16, etc. There's always an optimal value to the beam radius. We don't want this beam radius for the FSO link to be too small, because it will take you forever to go through a full scan. And then you don't want to make it too big, because if it's too big, then you become a little bit insensitive at the receiver end, and you will miss many times the fact that you locked on the signal. So you just have to find the nice sweet spot where basically you have an optimum beam radius. Now, just from a modeling perspective, we'll see that later on, we can have different types of distributions because, when you have this kind of model for R as a square root of x squared plus y squared, if you assume that these Gaussian are zero mean, zero variance, zero mean, same variance, you have a Rayleigh, but let's assume they assume that they have, and that's something we'll be using in our calculation later on, if they have zero mean, but you assume they have different variance, and that's very common in our type of application. You may have basically vibration in one dimension much stronger than the other dimension, like a HAPS, for example, can have a beam, a wind, like basically blowing in the horizontal dimension, so which means you may have much stronger vibration in the horizontal dimension than the vertical dimension, which means that sigma x and sigma y are not necessarily equal. So we'll be using in our calculation, as you'll see later on, a Hoyt type of distribution, which basically a case where we assume that we are nearly well aligned. You have a zero mean and average, but basically we have different variances. So now, just to tell you how nasty are these calculations, and this is actually our new results, although people have been looking at this problem for many years. So this is work with my collaborator, Dr. Yalcin Atta. We're able to derive the ouch probability of FSO link from ground to HAPS under this kind of Hoyt type of pointing error model and under gamma-gamma model, channel modeling. This is the closed form expression. Actually, it's just a finite range integral accounting for alpha and beta for turbulence and accounting for basically the QH, which is the pointing error imbalance, you may want to call it that way. So if QH equal to 1, which is you have balanced vibration, you have the same kind of vibration in the horizontal and vertical dimension, you can get rid of that integral and you end up having a full closed form expression in terms of alpha and beta. And of course, there is some pointing error parameter embedded here in eta S. Okay, so that's basically your ouch probability calculation from a ground to HAPS type of communication link, accounting for turbulence and pointing errors. We have done even for log normal, which, as you know, a much challenging distribution to deal with. And the result, again, in the case of QH general, which means like any kind of imbalance, is an integral from minus pi to pi, a finite range integral over a closed form expression. When QH equal 1, which means you have perfect balancing, you can even get a full closed form expression. So these are two new results that are available on arXiv and still going through the review process for a ground to HAPS type of connection. And I mean, they can be used also for ground to satellite. But the way we use them is to try to quantify how the performance in a ground to HAPS is affected by turbulence. So you see here, we are looking at an uplink, a downlink, and a horizontal link. So as you notice, the uplink in blue has the worst performance. Then in red downlink, you have, slightly better performance. And then the horizontal link is the best. This tells you that slant paths are more affected by turbulence than horizontal path for the very simple reason that turbulence tend to be more strong in lower altitude. At a certain point beyond 20 kilometers, actually turbulence becomes very negligible. And that's why a horizontal link between HAPS, let's say at above 20 kilometers, are basically unaffected by turbulence. And that's why you're hearing also for inter-satellite link being done in FSO, because in that kind of altitude, you don't have to deal with turbulence at all. Most of turbulence happening in the atmosphere between 0 and 20 kilometers, and the uplink is most affected because in the uplink, the optical wave gets hit very quickly by strong turbulence in its way to the air, whereas the reverse, the turbulence gets affected, gets stronger towards the end of the trip, and the end result is the out probability is more kind of degraded when you are dealing with an uplink type of situation. Now, if you use adaptive optics, as I mentioned earlier, you tend to see some improvements. So you see the diamond here. So the blue uplink without adaptive optics. With adaptive optics, you get a 5 dB gain roughly, or even more, thanks to adaptive optics for the uplink. Same for the downlink, you get some gain, and same for the horizontal link. Adaptive optics can help you get some gain and reduce or mitigate the effect of turbulence. Now, how can we use that in the context of hybrid, basically ground airspace? And I will try to be a little bit fast here to just remain within time and give time enough time for questions. So here we are trying to show how this concept of integrated ground airspace can be helpful in the context of FSO link. So let's assume you are trying to connect a ground station to a satellite via an FSO link. Typically, as I told you, this is not the way we do it. This is not very reliable. So usually you associate with an FSO link a backup RF link. The RF link will be operating at a much lower speed, but it's there to at least maintain certain level of connectivity. But now, recently, last year, there was an interesting paper proposing that actually, in order to further improve the performance of the FSO link, we can add an integrated space air-ground type of architecture where HAPS can be used as a relay. So HAPS, as you may recall, is going to be operating at 20 kilometer altitude in the stratosphere. So the idea is, let's say from an uplink perspective, you capture the signal after it went through its major kind of turbulence, which is from 0 to 20 kilometer, clean it up, decode and forward, and retransmit to satellites. They showed that that they get some gains. So we picked on this particular topic, and we start asking ourselves, what will be the optimal location for this HAPS? Should we place the HAP midway between the satellite and the optical gateway station, or maybe in another type of location, for example, exactly on the top of the optical gateway station? So that's kind of generic problem. So this is our HAPS. We are trying to see based, let's call this the so this is elevation, if you will, the component elevation is the azimuth angle. So the zenith angle, zenith angle. So you want basically to check at what zenith angle the HAPS should be operating. So based on our generic, derivation, we are able to kind of look at the end-to-end performance of these kind of links. So for instance, we can look at the parameter alpha and beta, which kind of give you an idea about the level of turbulence you are facing. So obviously from HAPS satellite, the level of turbulence is very weak. That's why alpha and beta are very high. I mean, alpha and beta, when they are high, meaning turbulence is low, okay? On the other hand, if you basically look, for example, at the proposed system in this 2021 paper, if the zenith angle becomes important, alpha and beta degrade quite a bit, which means you start seeing your FSO link subject to a lot of turbulence, and that's probably not a good idea. What we looked at is, what about if you place the HAPS exactly on the top of our optical gateway station? In that case, basically, regardless of the angle, we are always having or maintaining a constant alpha and beta from ground to HAPS. This has been actually, let's say, validated through our analysis. Remember some of the calculations I showed you earlier. So we looked here at the arch probability as function of a particular desired threshold below which we have bad performance, let's say. And we looked at this arch probability as function of different zenith angles. So you see here zenith angle between, let's say, ground and HAPS. So which is this angle here. Okay. Now, if this angle is 0, you get the best performance, which means placing the HAPS exactly on the top of the ground station is the best solution, although this link becomes longer, but that's a link that is going through a turbulence-free environment, which means it doesn't get basically degraded from turbulence perspective, and it seems that basically the end-to-end performance end up being quite good. But as this ground to HAPS basically zenith angle increases, then obviously from 10 to 20, 30, 40, you see a degradation in your basically outage probability. So this kind of inspire us to look at the designs where actually the HAPS have to be always on the top of the optical ground to station. So that's the desired design. And to conclude, we actually looked at the end-to-end arch probability. And to summarize our investigations, if you will, this is basically the hybrid RF FSO kind of benchmark, if you will. Now, if you add basically a relay as proposed a couple of last year, you get this 4 dB gain, but then if you place the relay optimally, you can get really a much bigger gain. That's kind of an interesting observation, and you can back up that with the RF, you can get some 2 dB gain. As an ultimate solution, I'll conclude with that, we studied this ultimate system where we have first a relayed FSO link backed up by a direct FSO link, further backed up by an RF link. The idea here is you want to maintain as much as possible FSO link connectivity in your integrated system, because FSO link give you higher speed and RF link give you always lowest speed, but maintain connectivity. And we showed that with this kind of system, obviously our proposed hybrid system has a certain average probability of error. The integrated system that we are proposing can give some extra diversity gain at low zenith angle, but at the large zenith angle, then this backup FSO link becomes to a certain extent useless because it's subject to strong turbulence, and that's why the performance of the system becomes the same. And as a conclusion, we can say the system that we're proposing is quite interesting, because if you look at this black curve, which shows the integrated SATCOM probability of RF link users, it's always the lowest, which means you're using most of the time FSO at highest speed. And this is the ultimate scheme is the most expensive because it uses 2 FSO link and 1 backup RF link, but it's the one that provides the best reliability and the best speed overall, at the expense, of course, the highest cost. So with that, I would like to thank you, and I will be happy to take some questions.
Thank you very much, Professor Alouini, for the very nice talk. So now we move to the Q&A section. So if anyone has any questions, feel free to write in the chat box. We have one question from Yosef Nasser from Green Wave. Actually, there are 2 questions. The first question is, FSO has been in the literature for some time. what is the status of the market therein?
Okay, I see the question in the chat. Thank you, Yusuf, for these two interesting questions. I agree with you. FSO has been around for quite a bit of time. You know, it started with military type of investigation. It went to commercial. Most of the applications have been targeting terrestrial application. Unfortunately, indeed, it didn't pick up in view of the very strong competition from the RF. As you can see, RF has a very strong expertise, skills, you can even talk lobby. And when you want to go to higher speed in RF, there's always kind of a full let's say, community environment that will push RF up. So as you know, as discussion for beyond 5G and 6G have started, a lot of people have been talking about terahertz communication. So one may argue, why are we really talking about terahertz, where basically terahertz suffer from pretty much the same issue that FSO suffer from, which is alignment issues, to a certain extent weather type of issues, but that's the way it is. I mean, there is a strong, as I said, lobby industry, let's say, in RF, and they will always try to make sure that they can always be competitive. So that's a fair competition. But on the other hand, that made FSO never, let's say, or until now, never be kind of a mass, doesn't have a mass market. You know, it's always a niche type of application for a terrestrial type of connection. Having said that, I do believe that for space and aerial application, FSO does have a big advantage because, first of all, you can never beat the speed of FSO. You can never beat the energy efficiency of FSO. In that case, you really need to be energy efficient, especially if you are deploying that to the top of hubs or satellite, where basically the energy budget is very important. So FSO can give you much higher speed for the energy that you'll be able to supply from these kind of aerial or space type of platforms. And that's why I believe aerial and space application is a niche area where FSO will outperform or will be having a strong competitive advantage compared to any other RF solutions. Now, the second, there'll be always a point where basically, and again, you should not look at it only from a competitive point of view. There will be a point where we'll be running really out of spectrum in this lower band, and FSO will complement the RF spectrum for terrestrial as well as for ground to space or ground to air type of applications. And that's what's happening in Ka band. So I just mentioned that Ka band indeed present good performance, but at the end of the day, Ka band now is under heavy competition from IMT. Some of these bands, people want to use them for 6G and for basic terrestrial cellular applications. And actually, Ka band is mostly used now for feeder link, and there is desire to start using Ka band for user link. And because user link now are using mostly Ku band, and that means that if Ka band start being used for user link, you need to start having different kind of band for feeder link or backhaul link, and then FSO can come and play that role. So again, it's if you look from a complementary perspective, from the fact that spectrum is finite and that you'll be always looking for extra spectrum resources, FSO can be there to provide a good solution, especially for air and space application, where it's not a massive market, but it's a niche market where basically FSO can bring big advantages. I hope I answered the two questions.
Okay, we have another question about what is the most deleterious noise source in a LEO FSO link?
Okay, so I think, I mean, noise, I don't think we call it noise, but I think what I mentioned in my presentation are the noise is the regular type of noise. You can even talk about sun radiation as one source of noise. But if you talk about like what are the source of main kind of issues, I think turbulence, as I mentioned, is a really big important aspect, because for LEO satellite, you need still to go through the atmosphere. So that first 20-kilometer layer can be a big issue that we have to deal with. So FSO, big problem is going to be atmosphere. Tracking, that's definitely a challenge. because especially for LEO satellite, they are not geostationary, so they are moving, and you need to keep tracking them. That's a big challenge, not unfeasible. There are companies like Mynaric in Germany, for example, they are able to do that, or the NICT in Japan, they are able to track satellites and or even airplane going at full speed. So it's not a problem, but it's quite expensive. Okay, and obviously with that, which I mentioned, I think in my talk, is weather, like fog and clouds. These are problems that will be facing any kind of ground to space or ground to air type of connection, and you need to have some kind of site diversity to mitigate that. So these, I would say, are some of the problems that are facing FSO for satellite type of connections.
Okay.
So there is another question. Do you think RIS can play a key role? So I think those of you who have been around in this seminar series for some time have seen a very interesting talk by Professor Robert Schober a few weeks ago, where he did talk exactly on this topic, how RIS can help FSO. And obviously, definitely, especially for, I would say, ground and terrestrial applications, one of the main limitations of FSO is that you can be blocked by a building or a hill or whatever kind of obstruction on your way. And the RIS can be there to bypass that. And Professor Robert Schober have done some great work and his team on the concept of RIS, which is, of course, very popular in the context of RF, but how to use that concept in the context of optical wireless communication, in particular in the context of FSO, to bypass basically obstructions.
Okay, in the other chat box, we have a question from Abdullah Al-Khalidi. And what will be the most practical wavelength for FSO?
So I think this is also a well-known topic. There are three, I would say, popular windows for FSO, as you know, but 1550 nanometers seems to be the most popular one for eye safety purposes. So anything below 1400 nanometer can be, having some, I would say, safety issue, especially for ground application, right? So 1550, which is above 1400 nanometer, has less concern from an eye safety perspective, and as such you can use laser with a stronger amount of power. And for this reason, I believe 1550 nanometer is probably the most popular FSO wavelength now.
Okay, thank you. Let me see any other question. I have one question. Actually, in the presentation, when you talk about mitigation techniques, you propose adaptive optics correction as yeah, but I think there are some other classical mitigation techniques to reduce the atmospheric turbulence. For example,
I mean, of course, you can use, of course, you can use aperture averaging. So you make the aperture bigger. That's, of course, one aspect. And this will, there are some calculations, you can recalculate the right of variance. So here, when you looked at the adaptive optics, basically, there's a famous book by Andrews, by the way, on this. And where did I put that formula? This formula is like for a fixed kind of altitude, but in practice CN square is function of altitude and function of the speed of the wind. There is like a model for that, and if you want to compute the right of variance, you need to integrate over the spectrum, the Kolmogorov spectrum, and in that you can account for adaptive optics. And then there are some other expression in this Andrews book where basically the right of variance can be deduced in the case of aperture averaging. So basically you have a different expression for the right of variance, you need to compute it, and then the right of variance, once you compute that, you can include that in your alpha and beta parameter that parameterize your gamma or log normal type of turbulence fading. So it goes back always to first, what are mitigation techniques you're using, how does it affect the right of variance, and there are some expression, for example, I mentioned the Andrews famous book, and then you can use adaptive optics, you can use aperture averaging, you can use in a way relaying. What has been used here is one mitigation approach, right? Like this idea of putting a relay is a way to decode and forward relay is essentially to clean up the signal, because most of the turbulence is happening in this lower part of the atmosphere, right?
Yes. Yeah. But
Yeah.
did you
MIMO,
compare with these other classical mitigation techniques? Did you compare the?
in our paper, actually, we looked at adaptive optics with in this context. If you look at the paper, this one.
Okay. Yeah, maybe.
It's an archive. Yeah, this one. We looked at adaptive optics. We didn't look at relaying, to be honest. No, just with and without adaptive optics in this paper.
Okay.
But in this other paper here, one second. Both are recent paper with we looked at with my collaborator Yalchin. I'm not sure. Oh, it's not here. We looked at this integrated systems, and no, not here. Yeah, this one. Yeah, the second one I think is available on Archive or TechRive. So basically, we looked at aperture averaging and relaying. So together, you know, so you can look at what is the although we didn't do like a kind of we didn't try to do a fair comparison, but we try to look at the effect of both relaying and averaging in the same type of analysis. So the calculation that we have, or the end results, can be used to make some comparisons.
Okay, thank you very much.
There is, of course, also for those of you who are familiar with the work of Murad Wisal, MIMO in the context of FSO. I talk about it here, but that's another way to mitigate effect of turbulence.
Yes, I think also some coding, special coding modulation schemes.
Yeah, you can use, I mean, the special code modulation, especially in the context of hybrid RF FSO, which I talked a little bit about here, but not really in detail. Like if you look at what I'm talking about here. So you have like a hybrid scheme, right? FSO and RF. So you can have either hard switching, which is moved from FSO to RF, or you can have a soft or like coding on both links. This is like called soft coding or soft switching, where basically there are some work that has been done on how you can code on two simultaneous channels to maintain extra reliability.
Yes. Yeah. Okay, we have another question about any comments on the latency of FSO staticon links. For example,
I'm not sure. Yeah, I mean, FSO probably will be, I mean, just because light propagates the fastest, will be always faster, but I'm not sure. In the ground, it has been used as an argument. Basically, you use FSO connection to, like there is this kind of company. I mean, like this was a few years ago, I would say even 10 years ago, where there is a company doing trading in Wall Street that used this FSO network on the ground to make sure that they have ultra low latency and beat everyone other kind of company in the same business. For satellite, I'm not sure that this is being used as a strong argument. I may not have seen all literature, but FSO always that doesn't suffer from latency because it's it's light propagating. So obviously there is no issues unless of course you are blocked by cloud or by turbulence or something like that.
Okay. Okay, Slim, let me see if we have more questions. I think we don't have more questions. I saw a message in the chat box about how you can be aware about these telecom seminars. Actually, we are announcing some mailing lists, but for those who are not receiving emails, please drop me a message and I can share with you the schedule for the rest of the year. Okay, so you don't have more questions. Maybe you are running out of time. And once again, I would like to thank Professor Alouini for the time and for this very nice presentation. We are recording all the seminars and we are making available in our YouTube channel, TII YouTube channel. So for those who want to see again or feel free to disseminate these seminars through your collaborators and researchers. So thank you very much, everybody. Thank you, Professor Alouini. And Hope to see you in 2 weeks in our next telecom seminar.
Thank you very much, Daniel, for the invitation, and thanks for all attendees. Thank you very much.